Have you ever wondered how we can actually see the incredibly delicate quantum information stored in a single atom? How do scientists peek at a qubit state without disturbing its quantum magic? Fluorescence readout in ion trap quantum computing is the ingenious method we use to determine the quantum state of an ion qubit by observing whether it emits light or not. It is essentially a way to optically measure the state of a qubit, translating its quantum information into a detectable signal. The core mechanism behind this relies on the distinct electron energy levels within an ion. Imagine an ion as having a set of shelves where electrons can sit. In an ion qubit, we typically encode the logical 0 and 1 states into specific, long-lived energy levels. To read out the qubit, we shine a laser tuned precisely to excite only one of these states, say the logical 1 state. When the electron in the logical 1 state absorbs a photon from this laser, it jumps to a higher and stable energy level. It then quickly falls back down to a slightly different intermediate level, emitting a photon of light in the process. This photon emission cycle can repeat many times, creating a shower of photons. Crucially, the logical 0 state is engineered such that this specific laser frequency does not excite it, meaning it remains dark and emits no photons. To perform the readout, a detector such as a photomultiplier tube or a CCD camera is focused on the trapped ion. A specialized laser, often called the detection laser, is then pulsed. If the ion is in the logical 1 state, it will fluoresce brightly, sending out many photons that the detector will count. If the ion is in the logical 0 state, it will remain just dark and emit very few or no photons. By setting a threshold, perhaps 1 or 2 photons, scientists can reliably differentiate between the logical 0 and logical 1 states. This process is repeated thousands of times to determine the probability of finding the qubit in each state. An intriguing technique used to enhance readout fidelity is called state-dependent shelving. Here, if the qubit is in one of its states, say the logical 0, it is first transferred to a completely different, very long-lived auxiliary state. Then, when the detection laser is applied, only the logical 1 state remains available to fluoresce. This makes the distinction between states even starker, pushing measurement fidelities well over 99%. It is like moving one of the options far away, so the light only interacts with the other. This incredibly precise and minimally invasive fluorescence readout is a cornerstone of ion trap quantum computing. It is what allows scientists to verify quantum operations, characterize qubit states after computation, and ultimately build confidence in the accuracy and reliability of these powerful quantum processors. The ability to clearly distinguish between 0 and 1 through light emission is not just clever physics. It is a foundational step toward unlocking the full potential of quantum information.
If quantum tech fascinates you, like, subscribe, and keep exploring with us.